Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show CFD analysis of a double pipe counterflow heat exchanger using SolidWorks flow simulation. The model consists of inner tube made up of copper and outer cooling jacket made up of brass, right? For better understanding of this drawing or model, let's see the sectional view of this model. This is the inlet of inner copper tube, and throughout the passage no restriction is there, and this is the outlet of copper tube. Inside this copper tube, hot acetone liquid at 56 degrees centigrade will be showing, and to cool this one, from here water will be passing at a specific rate, and the cold water inlet temperature will be 10 degrees centigrade, right? So let's see the things again. From this copper tube, boiling acetone will be showing with temperature of 56 degrees centigrade, and for cooling purpose we are providing water from here at a specific rate from the top of this cooling jacket, and the temperature of cold water will be 10 degrees centigrade. Okay, let's see the complete model view and let's get started. Now, as water and this acetone will be flowing through this counterflow double pipe system, so for viewing the flow particles it is better to make all the model to be transparent. Let's make the model transparent. The model is completely transparent. Now we can start our analysis, right? Okay, so what we have to do is, first of all we have to start with flow simulation and leads to be provided at the opening and closing ends. We are having two opening and two closing ends, so for that openings we have to provide leads, create leads. Yes, all the leads have been provided. The model is ready, right? Okay. Next one, we have to check the fluid volume, whether the geometry is okay or not. That we checked. Check geometry, and it will be an internal analysis. Check the geometry first. The status is successful, so geometry is okay. Now let's see the volume generated. So it is also okay. So our model is ready for analysis. Okay. Next we have to create an environment for flow simulation, and that can be done using wizard. The default name of the project as project 1 we are keeping. Next we are selecting SI system, and temperature will take as degree centigrade. Next, it will be an internal analysis, and we are considering heat conduction in solids. At the same time, gravity will be also involved, and also we can see in the drawing that actually gravity will be acting along y direction, right? In this case you can see this is y direction, gravity will be acting along y direction, so we have to provide along y it is minus 9.81 meter per second square, and along z axis it will be 0. Okay, next we want liquids. Liquids will be acetone will be passing through the inner copper tube, and another will be water as a coolant. We have taken two liquids, that is acetone and water. Next, we select the material. We are selecting material. The inner tube is made up of copper, and the outer jacket we'll take later on. Default wall thermal condition and roughness we're considering. Next, atmospheric temperature equal to 20 degrees centigrade. Concentrations we want to check again. So inside the copper tube initially it will be 100% acetone will be there, so its concentration is 1, and we are not providing any mixture of acetone and water, so concentration of water will be 0. That means initially inside the copper tube acetone will be there and no water is allowed initially. Okay, and let's select the solid parameters, temperatures. Solid temperature will also be 20 degrees centigrade as equal to atmospheric temperature. Okay, let's finish it. It is ready. Now this is our computational domain, right? Now all parts of our model should be inside our computational domain. To avoid any kind of mistakes, we make the domain little more compared to the existing one. So edit definition. While checking this computational domain, we have to see that it should not be very high and it should not be very low also. If the computational domain is very high, in that case calculation time will be more. Okay, our domain is ready. Now let's hide this computational domain, right? Okay. Next, what we have to show the fluid subdomains, because two fluids will be flowing. You have to show the locations of fluids. Let's take the segmented view of this assembly. First of all, we show the domain of boiling acetone, which will be having temperature of 56 degrees centigrade. Fluid subdomain, insert fluid subdomain. We have to take acetone and its temperature will be 56 degrees centigrade, right? Boiling acetone will be passing at 56 degrees centigrade. So we'll select the location of that one. This is the domain of boiling acetone at 56 degrees centigrade. Okay, close it. Another domain is required for cold water. Insert fluid subdomain. We want water and at a temperature of 10 degrees centigrade. It will be passing from the top of this brass tube. Okay, done. So this is the domain for cooling water. Okay, we have defined the domains. Next, we have to show the solid materials. We have to define. Insert solid material. Predefined. We have already defined for copper tubes. Let's do it again. Copper tubes. So we have to select that copper tube again. What can we do is we can go back to the original model and select that copper tube again. Copper tube selected. Done. Next one, the outer cooling jacket should be provided. Solid materials, insert solid material. Predefined. We're taking brass for this outer cooling jacket. To select that outer cooling jacket. Done. So brass is provided. Okay, done. Now boundary conditions. Again, for application of proper boundary conditions, it is better to select the segmented view. So we are not changing the view, it is segmented. Boundary conditions. Insert boundary conditions. Inlet mass flow rate and thermodynamic parameters. We want to provide acetone at 56 degrees centigrade. Temperature will be 56 degrees centigrade and substance concentration will be 100% acetone and water 0, right? And mass flow rate we have to provide at 0.001 kg per second, and the location of this acetone will be from here. Okay, done. Next one, the cooling water to be provided. Inside boundary conditions, mass flow rate will be, to provide more mass flow rate, 0.05 kg per second, and thermodynamic parameters will see it will be having 10 degrees centigrade water, and substance concentration, it will be 100% water. So acetone will be 0 and water will be 1. Okay, now the location to be provided, it will be passing from this location. Grain check, done. Now two other boundary conditions are also needed, that is the atmospheric pressure at the exit ends, right? Okay, so boundary conditions, insert boundary condition, it will be environmental pressure at the exit end of acetone. Done. Grain check. Again, another to be provided for cold water. Boundary conditions, insert boundary condition, environmental pressure at the exit of cooling water. Grain check. It's done. We can provide some convective heat transfer coefficient for the cooling jacket also. Let's provide that one. Boundary conditions, insert boundary condition, walls, we want real walls. The outer wall will be having convective heat transfer coefficient equal to, let's say take this one as 60 watt per meter square degree Kelvin, and temperature will be 20 degrees centigrade. And you have to select that wall, cooling water pipe we are selecting, done. So our model is ready. Next one, we have to provide some goals, right? Insert some surface goals. When you see average temperature of fluid at both the exit ends of water and acetone. First one, we are taking average fluid temperature at the exit end of acetone. So select other, lead number 2, grain check. Another goal is required. Goals, insert surface goals. We want to take same thing like average temperature of fluid, that means average temperature of what? Cooling water at the exit end, right? So this is the exit end of cooling water. Select other, lead number 4, grain check. Another equation goal we want to see the difference of both the exit ends, right? Select equation goal, insert an equation goal. It will come from these goals. So average temperature of fluid 1, that is for acetone, minus average temperature of water. Okay, so equation goal is defined. All the goals have been defined properly. Now we can go for our running, right? You run this one. Okay, let's run it. You can see the solver window, it has started running, it is ready, it's preparing the model, it is continuing. Let the iterations move on. Whenever it finishes, we'll see the results and analyze. Okay, the solver window has finished its calculations or iterations. Before seeing the results, let's analyze it from the solver window itself. We had 3 different goals, 2 surface goals and 1 equation goals. We'll see one by one. We can see all of them together also. First one, we're going to see that temperature of exit end of acetone. Okay, it started with 56 degrees centigrade and it has conducted near about 300 numbers of iterations. After 300 numbers of iterations, its value has come down to in the range of 53.78 degrees centigrade. Okay, so it has reduced very less only. So we should provide better cooling, right? Initially the temperature of acetone was 56 degrees centigrade and after 300 numbers of iterations, its temperature has reduced to 53.78 degrees centigrade. Okay, let's see the other goal. See the temperature of cold water. It started with 10 degrees centigrade and at the end of 300 numbers of iterations is coming down to 11.53 degrees centigrade. You can see the nature. So from 10 degrees centigrade it has gone high, then again it has reduced, right? Okay, now we'll see the equation goal, that is the difference of these two temperatures. Initially the difference of these two temperatures was 45 degrees centigrade and finally it has come down to in the range of 42 degrees centigrade, right? Okay, let's see the results from cut plots. Results, insert cut plots. We see temperature distribution along front plane, temperature fluid we want. Okay, so it is showing that initially the temperature of this acetone is very high in the range of red, that is 56 degrees centigrade. As it is approaching towards this pipe, its temperature is coming down, right? So you can see clearly it is at the beginning it is 56 and as it is approaching towards its path, its temperature is reducing from yellow zone to green zone and finally blue zone, right? You can see the different zones. Yellow zone is in the range of 37 to 46 degrees centigrade, green zone from 28 to 37 degrees centigrade. Even at the exit end also you can see the temperature of acetone is in the range of green zone, right? Here is the green zone because here we are not putting any kind of cooling. Okay, now we'll see this one in the form of an animation. Let's see cut plots 1 animation. First clear and hide this part. Cut plot 1 animation. Let's play. Okay, now I want to see this one from other plane. Let's see this cut plot along right plane. Cut plot 1 clear and hide. Cut plot 1 edit definition. I want to see from right plane. So select the plane, right plane. We can move this one a little bit inside. Again check. We'll see the cut plot, that is at the midpoint. You can see here this is the temperature distribution, right? We'll show this one in animation also. We'll see this in the form of animation also. Better to see from that plane side view. Okay, let's clear and hide this part. Now want to see surface plots along all surface. Insert surface plot. We'll see the isometric view. Use all surfaces and you want to see temperature of fluid. Grain check. It is showing the temperature distribution along the different all surfaces. You can see from here also, right? So this is actually showing for outer surface of this cooling jacket, and this is for actually for our acetone, right? Okay, done. Now we want to see that flow trajectories, that is how these flow particles will be moving inside these pipes, right? Surface plots, clear and hide, then flow trajectories, insert. We will see temperature of fluid, let the number be 50, and we want to see in the form of arrows only. And we want to show the locations. We will see both the locations of this acetone and water. Select other, and it is lead number 1. Done. We want to show the location of water also. Select other, and lead number 3. Done. Grain check. Okay, it is done. Now we can see it. Right, okay, let's see it. Now I want to see in the form of an animation, and this is for fluid temperature. You can see pressure also, everything can be seen, but want to see in the form of an animation, right? So flow trajectories, clear and hide, flow trajectories, play. In the counter flow, you can see that means water is flowing one direction and this acetone is also flowing in some other directions. You can see flow of water in this direction and acetone is flowing this direction. In the acetone flow, we can see some kind of turbulence is there. That can be controlled using the mass flow rate of acetone, right? Is clearly visible, the flow particles. Let's see this one at the critical phases. So water is flowing from top to bottom, and here you can see a little bit of turbulency. Some backflow is also there. This acetone is moving from here to the exit end. A little bit of backflow is occurring. That depends on a lot of conditions. We can change this pattern also by proper control of this acetone flow rate and its temperature also. At the entry of this acetone, let's see what it is happening. Let's see. So we can see here clearly some kind of turbulence is there. It is coming back again and going in this way, right? acetone is passing from this way. This is the inlet of acetone. Here's some kind of backflow we can check. So we can modify this design. Maybe we can feel, what we feel is some kind of problem is there at the exit end of this acetone, because here you can see some kind of backflow is occurring. This is all about today's analysis of double pipe counterflow heat exchanger. The parametric study and optimization part will be done in another video. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.